Okay, recall that we had an inductor consisting of a coil of 300 loops over 10 centimeters with a 3 square centimeter cross-sectional area, and we calculated a magnetic field based on the assumption that the magnetic field was uniform along the x-axis between 0 and 10 centimeters, and the contribution of the rest of a loop would be 0, so that we calculate the inductance by the line integral around the loop, and the magnetic field by the line integral around the loop, and we simply get the amount of current penetrating 300 loops at 12 amps gave us a certain magnetic field, and that magnetic field times the 10 centimeters should equal 4 pi k times, or mu naught if you prefer, times the current that penetrates the loop, and from that we calculated an inductance of 3 times 10 to the negative 5th Henry. Now that was already done, just wanted to review that. The assumption that the magnetic field is uniform within the set of coils isn't particularly accurate, as we said before. If you move away from the central axis, the field varies, and as you get toward the edges, the field varies, or toward the ends of the loop. That could be remedied by putting the inductor in a toroidal configuration, a donut shape. Imagine a donut surrounded by a bunch of wires. Then we wouldn't have the end effects. Everything, the entire magnetic field would be contained within, and you see that in your text. The analysis is very similar to the analysis we used here, and it's more valid than this. Bottom line, though, is when you have an inductor, you can't really do it. You can't really determine the inductance all that accurately with great precision, say. Theoretically, you just got to build the thing and measure it. But you can get pretty close. You can get pretty close. So this isn't too far off. You know, this may be off by 20% from what you would actually get. Okay. We want to get the field energy per unit volume, and that's the question. We calculated the field energy when the current is 0.0012 amps, which would be the current if we had a 10K resistor in series with this inductor and a 12-volt source. The field energy is calculated easily. You're just integrating the voltage with respect to the current, the voltage being Li. So you integrate Li with respect to I, you get Li squared over 2. And here's your field energy. We calculated this previously as well, I believe. What's the energy per unit volume? Well, the volume of this coil here is simply the cross-sectional area, 3 square centimeters, multiplied by the 10 centimeter length, 30 cubic centimeters, or 300 thousandths, 0.0003, 3 times 10 to the negative 5th cubic meters. We divide the energy by the volume, and we get the energy per unit volume. Very small energy per unit volume in this case, 7 times 10 to the negative 7th joules per square meter. Now this is with a very small current. If we go back to the current we used in the initial analysis of the circuit, as a 12 amp current, then this thing becomes 10 to the 4th times as great. The current becomes 10 to the 4th times as great. Its square becomes 10 to the 8th times as great. The magnetic field becomes 10 to the 8th times as great. And your energy becomes 10 to the 8th times as great. This 10 to the negative 11th would be a 10 to the negative 3rd. And putting that here and dividing by this, we would get 10 to the 8th times as much energy per unit volume, or about 70 joules per cubic meter. And that would correspond to a field of, I believe the field with 12 amps was 4 times 10 to the negative 7th Tesla. Yeah, that's a fairly significant field. And that field would contain energy, field energy, 70 joules per cubic meter. Okay, well, that's the energy per unit volume. This can be done symbolically. And the symbolic solution, the symbolic energy per unit volume is actually comes out fairly simply is B squared over 2 mu naught, or B squared over 8 pi K prime. And you can follow the derivation. We've derived the expressions in terms of the current and the inductance. In terms of the current and the inductance, we can get the magnetic field and express the result in terms of the magnetic field. We've done the symbolic, but we've not done the symbolic analysis to get to this point. We've come up one step short of getting this, but you'd be able to follow this easily enough in your text.